Welcome to the deep dive. We're diving into the quantum realm today. It's going to be a wild ride. We're tackling the measurement problem, one of the biggest head scratchers in physics. How does the uncertain world of quantum possibilities become the solid reality we experience? We'll be dissecting a fascinating article that grapples with this very question.
It's a question that has puzzled physicists for almost a century. How do we go from the fuzzy world of quantum mechanics, where particles exist in a haze of probability, to the concrete world, where things seem to have a definite place in time?
Yeah, it's bizarre, right? Like, in the quantum world, things aren't so clear-cut. Imagine losing your phone. In the normal world, your phone is lost in one spot. But in the quantum world, it's like your phone is potentially everywhere at once until you find it.
That's superposition in a nutshell. It's a cornerstone of quantum mechanics. It's not that we don't know where a particle is. It genuinely exists in multiple states simultaneously, kind of spread out like a wave of possibilities.
So it's not just hiding under the couch cushions. It's like it's under the couch in the fridge and maybe even on the moon all at the same time. That's wild. But this isn't just theoretical mumbo-jumbo, is it?
Not at all. The double slit experiment shows this. Imagine shining a beam of light at a barrier with two tiny slits. Common sense says you should see two bright spots on a screen behind the slits.
Right. Light travels in a straight line. Two slits, two spots of light. Seems straightforward.
But you actually observe an interference pattern, as if the light is behaving like waves going through both slits at the same time and then overlapping. This experiment and many others show that particles like electrons can act like waves spread out in space. They defy our classical intuition.
Okay, so light can act like a wave and a particle. Electrons are doing the wave thing too. The quantum world is playing by a whole different set of rules. But how does this lead to the measurement problem?
Well, think about it. If particles exist in this blurry state of superposition, what happens when we observe them, when we try to measure their properties? Why do they suddenly snap into a single definite state? Why does the wave of possibilities collapse?
So before we look, it's a wave of potential. But as soon as we peak, the universe says, okay, gotta pick one. Let's go with this one. That sounds almost arbitrary.
It does, doesn't it? And that's the heart of the measurement problem. What triggers this collapse? Is it the act of observation itself? Does consciousness play a role? The article we're looking at today offers a unique perspective. It distinguishes between the quantum world, what it calls a physical universe, and our everyday reality, the corporeal world of our senses.
Hold on, corporeal world. You're losing me a little. Can you break that down?
Sure. Think of it this way. The corporeal world is the world we experience directly through our senses. Colors, textures, sounds, qualities, not just quantities. The quantum world, the physical universe, is described by mathematical equations, probabilities, and abstract concepts. Beyond our direct sensory perception.
Okay, I see the distinction. So there's the quantum world of pure potential, and then there's the world we experience, which is somehow a filtered version of that.
Exactly. And the author argues that this distinction is key to understanding the measurement problem. They suggest that our usual way of thinking about cause and effect, what we call horizontal causation, simply can't explain the instantaneous collapse of a wave function when a measurement is made.
Horizontal causation. Sounds like we're venturing into philosophy here.
Well, physics and philosophy often intersect when dealing with questions about the fundamental nature of reality. Horizontal causation is simply the idea that causes precede effects in a linear fashion, like a chain of events unfolding over time. It makes sense in our everyday world, but it struggles to explain the quantum world.
Okay, I'm with you so far. So if horizontal causation can't explain the sudden collapse of the wave function, what can?
The article proposes a rather bold idea: vertical causation. It's a concept that will definitely stretch our imaginations. Imagine watching a movie. The events on the screen unfold in a linear way, scene after scene. That's like our experience of time, a straight line from past to present to future. That's horizontal causation.
Makes sense. Cause and effect as a step-by-step process.
Now imagine stepping outside of the movie. Instead of watching it frame by frame, you see the entire film all at once. Every scene, every moment existing simultaneously. That's a glimpse into the realm of vertical causation, a realm outside of our ordinary perception of time.
Whoa. So instead of cause and effect along a timeline, it's like it's all happening at once from some higher dimensional perspective.
Precisely. And from that vantage point, the collapse of the wave function wouldn't be this sudden, mysterious event. It would be a natural consequence of the interconnectedness of all things.
So vertical causation suggests that the quantum world isn't bound by our linear understanding of time. It's like the universe is playing a cosmic symphony and we're just hearing one note at a time.
That's a beautiful way to put it. But this idea of vertical causation, Is there any evidence to support such a radical concept?
That's what I was wondering. It sounds pretty far out there.
Here's where things get really interesting. Remember the 2022 Nobel Prize in Physics? It was awarded for experiments on entanglement, a phenomenon that even Einstein called spooky action at a distance.
Entanglement. I've heard the term. Can you remind me what it is exactly?
It's when two particles are linked in a way that defies our classical understanding of space and time. Imagine two coins flipped at the same time. In the classical world, if one lands on heads, the other would be heads or tails right.
Right, 50-50 chance. Basic probability.
But with entangled particles, it's as if the two coins are magically connected. If one lands on heads, the other instantly flips to tails, no matter how far apart they are. It's as if they're communicating instantaneously faster than the speed of light.
Wait a minute. Faster than the speed of light. Isn't that impossible according to Einstein's theory of relativity?
That's the mind-blowing part. These experiments challenge our fundamental assumptions about the universe. They tested what are called Bell's inequalities, which basically set limits on how correlated two particles can be if they only follow the rules of classical physics. The experiment showed that these limits were violated, meaning something extraordinary is going on.
So these experiments prove that entanglement is real, and it can't be explained by the physics we know and love.
Exactly. And that's where vertical causation comes in. It offers a potential explanation for this spooky action at a distance. Instead of information traveling faster than light, it suggests that the entangled particles are connected outside of our familiar notion of space and time. It's like they're two sides of the same coin, always linked, even when separated by vast distances.
That's incredible. It seems like entanglement could be a window into this realm of vertical causation, this hidden dimension of reality where everything is interconnected. But let's come back to the measurement problem. How does vertical causation actually solve it? If we're observing things outside of time, does that mean our observations don't really matter?
That's a great question. And it gets to the heart of the debate about the role of the observer in quantum mechanics. The article doesn't claim to have all the answers, but it does suggest that vertical causation could provide a framework for understanding how quantum possibilities become classical realities, without invoking consciousness as the sole trigger.
Okay, so maybe it's not about us choosing a reality with our observations, but rather about this deeper level of interconnectedness that determines how the wave function collapses.
That's one interpretation. The article invites us to consider a perspective where the collapse isn't a sudden event, but a process woven into the very fabric of space-time orchestrated by this vertical causation. It challenges us to expand our understanding of causality and recognize that there may be forces at play that operate beyond our current scientific framework.
This is seriously mind-bending stuff. It makes you wonder if our everyday reality, the world we perceive, is just a tiny sliver of a much grander interconnected reality, operating by rules we're only beginning to grasp.
Exactly. It raises a lot of profound questions. If our perceived reality is just the tip of the iceberg, what lies beneath the surface, what are the implications for our understanding of the universe and our place within it?
If our observations are part of this interconnected dance, does that change how we should approach the world around us? Does it give us a greater sense of responsibility for the reality we're co-creating?
Those are questions worth pondering. The measurement problem isn't just a scientific puzzle. It's a philosophical exploration of the very nature of reality and our role as observers.
It really makes you wonder, if we've been thinking about reality all wrong. What if instead of a fixed objective world out there, reality is more like a dynamic process, a dance between the observer and the observed?
It is a profound shift in perspective. The measurement problem and quantum mechanics in general, they challenge us to move beyond the deterministic worldview of classical physics and embrace a reality that is fundamentally uncertain, interconnected, and perhaps even participatory.
Yeah, it's like we're not just passive bystanders. We're active participants in shaping the world around us. That's both empowering and a little daunting, don't you think?
Absolutely. It raises all sorts of questions about our role and responsibility in this cosmic dance. If our observations contribute to the collapse of the wave function, does that mean we have an ethical obligation to observe consciously, to be mindful of the impact our choices and actions might have on the unfolding of reality?
Those are some heavy questions. It's almost like we're being asked to step into the role of co-creators, shaping reality with our very presence and awareness.
And that's what makes the study of quantum mechanics so fascinating. It's not just about understanding the physical world. It's about understanding ourselves, our consciousness, and our place in the grand scheme of things.
So it's not just about electrons and photons. It's about us, about the human experience, and our connection to something much larger than ourselves.
Precisely. The measurement problem with all its mysteries and paradoxes. It invites us to embark on a journey of self-discovery, a quest to understand not only the nature of the universe, but also the nature of our own minds.
We've covered a lot of ground today. We started with the perplexing behavior of quantum particles, explored the mind-boggling idea of vertical causation, and ended up contemplating the very nature of reality and the role of consciousness.
It's been quite a deep dive indeed. And even though we haven't solved the measurement problem, we've gained some valuable insights along the way.
Yeah, we've certainly expanded our perspectives and maybe even stretched our minds a bit. So for our listeners who are now contemplating the nature of reality and their place in the universe, what's the one key takeaway you'd like them to remember?
I think the most important lesson is that the universe is full of mysteries, and that's okay. Embracing the unknown, questioning our assumptions, and being open to new ways of thinking, those are essential for expanding our understanding of the world around us and within us.
I love that. Embracing the mystery. It's a reminder that the journey of discovery is just as important as the destination.
Absolutely. And who knows what groundbreaking discoveries await us as we continue to explore the quantum realm. Maybe one day we'll crack the code of the measurement problem, but even then, the quest for knowledge and understanding will continue.
Well said. So until our next deep dive into the fascinating world of science and beyond, keep those minds open, keep asking questions, and keep exploring the wonders of the universe. And remember, reality might just be a collaboration. So observe, consciously make those choices with intention, and let's see what we create together.